Lesson 8-7, Polynomial Functions. A polynomial function is just like a polynomial expression with one major difference, and that is that the expression has been set equal to something. This is known as a polynomial equation or a function, and when referring to a polynomial function, we specifically mean an equation of the form f of x equals any polynomial expression with only the variable x. So you can't have any other, it's just a single variable. It doesn't have to be x, but just any single variable. And that variable will match this variable. In addition to f of x, we can also use g of x, h of x, or any other letter to differentiate between different polynomial functions. Of course, we wouldn't really use x because x of x would be confusing. Zeros. Following are some examples of polynomial functions. F of x is equal to 3x squared plus 2x minus 15. G of x is equal to 2x minus 18. H of x is equal to 9x to the fifth minus 4x to the fourth plus 6x to the third minus 12x squared minus 6x plus 1. So they can be short or they can be long. These functions can be graphed and solved just as we were able to graph and solve linear functions. For example, g of x is equal to 2x minus 18 is linear. And that is because there is no exponent. The solutions to the polynomial functions are known as solutions, roots, or zeros. So those three words are interchangeable: solution, root, and zero. The solutions are called zeros because they're the point at which the graph of the function hits or crosses the x-axis and the y value is 0. And they can be found by setting the function equal to 0 and solving the resulting equation. So finding the zeros. The first thing is we'll set the polynomial equal to 0. So instead of being f of x is equal to x squared plus 7x plus 12, I'll make this x squared plus 7x plus 12 is equal to 0. Then we factor the polynomial. Use a method that we've discussed earlier. I want two terms that will add up to make 7 but will multiply to make 12. And that gives me 3 and 4. So this will factor to x plus 3 and x plus 4. The next step is to set each of the factors equal to 0. So x plus 3 is equal to 0, x plus 4 is equal to 0. And then we solve each resulting equation. So I'll subtract 3 from both sides to get x is equal to negative 3. I will subtract 4 from both sides to get x is equal to negative 4. And my solutions are negative 3 and negative 4. Now you'll notice I'm using braces and not parentheses. And that is because this is not a coordinate pair, this is a solution set. Okay, we're going to solve the following polynomial functions. So I have f of x is equal to 3x squared minus 10x minus 8. So I'm going to multiply 3 and negative 8. And that is going to give me negative 24. And so now I'm going to look for two numbers that will give me a negative 24 when I multiply them and a negative 10 when I add them. Now because the 24 is negative, I'm going to have one negative factor and one positive factor. Sorry about that. Okay, so I'm looking for two factors of 24 that will have a difference of 10. And that's 2 and 12. And because I want my 10 to be negative, I'm going to make my 12 negative. I replace the negative 10 with a 2x and a negative 12x. And then I'm going to factor by grouping. Sorry, I forgot to set that equal to 0. Got stuck up on the factoring and completely forget that important part of the setting equal to 0. That's very vital. So I get x minus 4 times 3x plus 2 is equal to 0. So that gives me x minus 4 is equal to 0 and 3x plus 2 is equal to 0. Solving each of these, I get x is equal to 4. And x is equal to negative 2/3. So my solutions are 4 and negative 2/3. Now here I have a polynomial with 4 terms. I'm going to go ahead and set that equal to 0 and not forget that this time. And I'm going to factor by grouping. I can take an x out of the first. I did not do that correctly. Hold on a moment. I just realized that I mistyped that. It should be a 3. What on earth did I do there? Okay, yeah, I went back and checked. That's meant to be a 3. Sorry about that. Set it equal to 0. I can factor an x squared out of the first term, and that gives me x plus 3, and I can factor a negative 9 out of the second, and that gives me x plus 3. Now when I factor this out, I have a difference of squares. So I have x plus 3, and then x plus 3, x minus 3 because of my difference of squares. Now these factors are repeating, so I don't have to solve that twice. And so I get x is equal to negative 3 and x is equal to positive 3. So my solutions are 3 and negative 3. Okay, graphing polynomial functions. We're going to sketch the graph of a polynomial function. This can be achieved in 2 ways. In the first, we can use a t-chart and we can find multiple points to connect with a line or a curve. This can be very time consuming, and if we don't obtain enough points, we may misrepresent the graph. So even if we're using the t-chart method, we need to know some of the basics. We need to cover the basic shape of the polynomial functions based upon the degree. And remember, the degree is the highest exponent. And then we talk about the end behavior of the graph. And then when we combine these with the y-intercept and the zeros, it can help us sketch the basic shape of the graph without plotting multiple points. We can look at the basic shape of the graph of a polynomial function by degree. If we have a degree of 1, basically that means there's no exponent appearing. We have a straight line. If we have a degree of 2, we have a U or a parabola. If we have a degree of 3, we have something similar to this. Degree of 4. Or that could be flipped over. Degree of 5. degree of 6, degree of 7, and degree of 8. Now what you may or may not have noticed is that if we look at the x-axis, we are crossing or hitting the x-axis in the same number of points as our degree. So here we'll have 5, here we'll have 6, 7, 8, etc. This is what tells us the basic shape of our graph. Now it may not be as curvy as this. For example, a third degree polynomial will often look like that. It can be more stretched out, but this is the basic idea. Now the other thing we need to know about our function before we can graph it is what the end behavior looks like. And the end behavior of the graph refers to the direction that the ends of the graphs point, up or down. The direction can be determined by looking at the leading coefficient, which is the number on the first term, and the exponent. For example, if the leading coefficient is positive and the exponent is even, then both ends of the graph will point up. So for example, if I have f of x is equal to 2x squared plus 3x plus 1, both ends of my graph will point up because I have a positive and an even. Okay, when we talk about the degrees of the polynomial and the leading coefficient, this is what ends up happening. If we're even and positive, the function approaches infinity, so it goes up as x is negative, and it goes up as x is positive. So both ends are up. So an example of a graph would be like our parabola we just looked at. Now if the degree is even, so the exponent, this is the exponent, but the leading coefficient is negative, then as x is negative, the function is also negative, and as x is positive, the function is also positive, so both ends go down. So if we had a 4, both ends would go down. Now, if the exponent is odd and the leading coefficient is positive, what happens is as x is negative, the graph goes down, and as x is positive, the graph goes up. So they match. Negative is negative, positive is positive. But if we're odd and the leading coefficient is negative, that flips around. So as x goes negative, the graph goes up. And as x goes positive, the graph goes down. So basically, we get the opposite effect. There's something wrong with my pen. Okay, so let's sketch the graph of this function. We need to know the zeros, so we're going to have to solve it, which we actually already did, so it'll be easy to solve again. We first set it to equal to 0. then we factor it. And when we factored it, we got 3x plus 2 and x minus 4. And when we set each of those equal to 0, we got x was equal to negative 2/3 and x was equal to positive 4. Next, we want to look at the leading coefficient. Is positive, and the exponent is even. This means that both ends go up. So when we graph this, we're going to put a dot on 4. We're going to put a dot at negative 2/3, which is roughly here. And we know that both ends are positive, so it's going to do something like this. Now, this may not be the exact, this is just the basic idea. I don't know how far this dips, but I know that it's going to go between these 2 points and it's going to dip down. Now, if you recall, my next example, I had mistakenly typed a 4 when it should have been a 3. So we will fix that. And if you recall again, when we graphed it, we had x plus 3, or we factored it, sorry, x plus 3, x minus 3. So that gave us that x was equal to 3 and x was equal to negative 3. Now our leading coefficient is equal to 1. It's positive. And our exponent is odd. Now when this occurs, when we have an odd exponent and a leading coefficient, our negative will go down and our positive goes up. So I'm going to put a dot at negative 3, and I'm going to put a dot at positive 3. And there's going to be something else that has to happen in here. This is a terrible example. Okay. Sorry, I did not pick a great example here. But we are still going to have that kind of loop. I don't know exactly what it's going to look like, but I do know that I'm going to have some sort of a loop here, because this is going to have to go down and this is going to have to go up. So if we undo and we figure this out, so this has to go down, this has to go up, and something has to happen in between here. Well, what we do is we curve this out and we bring that up. Okay, when we graph parabolas, like our first example, all second-degree polynomials will have the same basic shape, which is a U. And there's a method for graphing a parabola accurately that we can do without having to create the table of points. And that involves finding the following: the y-intercept, the axis of symmetry, and the coordinates of the vertex. Okay, so a polynomial function is known as a quadratic function, and it will always be of the form f of x is equal to ax squared plus bx plus c. Now a can equal 1, but a can equal negative numbers, but a cannot equal 0. The axis of symmetry was that vertical line that passes through the center of the parabola, and it cuts the parabola into 2 mirror image sides. So they're identical on both sides. The equation for the axis of symmetry is x is equal to negative b over 2a. This gives us that vertical line. And then we find the y-intercept by setting the function equal to y. We plug in 0 for x and then we solve it. And then we can find the coordinates of the vertex by plugging in the value of x from the axis of symmetry that we found up here and solving for y. And that will give us the coordinate x, y. This x and this x will match. Once the axis and points are determined, the parabola can be graphed. Okay, graphing the parabola. We're going to graph the parabola x squared plus 4x plus 3 using the method we just discussed. Oops, sorry about that. So the first thing we want to do is find the axis of symmetry. And the axis is x is equal to negative b over 2a, which is negative 4 over 2 times 1, since a is invisible 1. That gives me negative 4 over 2, so that's negative 2. Okay, so that means our axis is this line here on x equals negative 2. And usually I do that in red or a highlighter or a light pencil, so I know that it's not actually part of the graph, it's just my axis of symmetry. Then the next thing I do is I find the y-intercept. To do that, I set the equation equal to y. And I plug in 0 for x. I'm having a hard time with this pen tonight. So I get 0 plus 0 plus 3, so y equals 3. And then I find the vertex. Now I already know the x coordinate is negative 2. I just need to find that y coordinate. So again, setting the equation equal to y, I plug in negative 2, I square it, plus 4 times negative 2 plus 3. So I get 4 minus 8 plus 3. 4 minus 8 is negative 4, plus 3 is negative 1. So my vertex is the point negative 2, negative 1. Now, I plot these 2 points, the y-intercept, which is x is at 3, or sorry, y is at 3, and then the vertex, which is negative 2, negative 1. Now, I said the axis of symmetry gave us a mirror image. That means that if I'm 2 spots away on this side, I am 2 spots away on this side. So this distance and this distance will be the same. So 2 and 2. And now I connect my 3 dots with a curve to make a U. And that's how we do that. Let's try one more. The next thing I find is my y-intercept. Two times 0 squared plus 7 times 0 plus 3 gives me that y is equal to 3 again. And then I find my vertex. And we know that x is negative 1 and 3/4. Or I'm going to use negative 7/4 to plug in. I'm going to have 2 times negative 7/4 squared plus 7 times negative 7/4 plus 3. So that's going to be 2 times 49/16 plus negative 49/4 plus 3. 16 divides by 2, that's going to give me 8. So I'm going to have 49/8 minus, I'm Now I need to turn this fourths into eighths to be able to add these together. So I'm going to multiply both the 49 and the 4 by 2. And I'm going to get 98 eighths. And then I need to turn this 3 into eighths, so I'm going to multiply it by 8. So I've got 49 minus 98 plus 24. That is going to give me negative 25 eighths, which for the purpose of graphing is negative 3 and 1/8. So just about negative 3. So now I'm going to graph my y-intercept, which is at 3. I'm going to graph my vertex, which is going to be just a little bit below negative 3. Now, I am 1 3/4 this way. So here I go 1, and then 3/4 will bring me to the halfway point. So that's how I know I'm even. And then I'm going to connect my dots with a U.